Okay, next type of functional group is an alkyne. So we've seen alkanes, alkenes, now we see alkynes. So alkynes are hydrocarbons that have at least one triple bond, okay? They might have some other stuff happening too. They could potentially have a double bond. They're definitely going to have some single bonds in there, but for the most part, we're looking that they are going to have a triple bond. So general formula-wise, these ones are CN. What is happening? Sorry, let's fix that up. Okay, these guys are CnH2n minus 2. Okay, so we saw alkanes, which was all single bonds with CnH2n plus 2. Then we had alkenes, which was CnH2n, and now we have alkynes, which are CnH2n minus 2. Okay, so even fewer hydrogens because now we've put that triple bond in place. So we have talked about aliphatic, and these are still going to be aliphatic because they still don't have that special something that makes something aromatic, okay? Similar to alkenes, these are also unsaturated. Okay, reason they're unsaturated, same one as alkenes. We have some triple bonds in here. Not everything is a single bond, okay? So your biggest differentiation between saturated and unsaturated is everything a single bond or is it not? If every carbon-to-carbon bond is a single bond, you have something saturated. As soon as you have some carbon-to-carbon bond that's either a double or a triple, you are now into unsaturated territories, okay? So naming alkynes, exactly the same as naming alkenes, okay? We're going to use a number in front of that suffix to indicate to us where that triple bond is. In this case, obviously the suffix is going to be -ine, because we now belong to the alkyne family. Difference, that order of priority. Remember we started talking about that when we were dealing with alkenes, and then we said order of priority, again, only for tie. No tie, don't care, I only care about a smaller number. But if I have a tie, my triple bond comes first, my double bond comes second, and then I'm going to go alphabetical side chains. Okay, so only other thing that could potentially be different. What if I have a double bond and a triple bond? Then I have two things that need to go in the suffix. Okay, what you're going to do, same thing you did in a prefix. If you had two things that had to go in a prefix, right? Like if we had two side chains, we put those in alphabetical order. We're going to do the same thing here. If we have a double and a triple bond, we're going to put them in alphabetical order, so the -ine is going to come before the I. Also similar to our alkenes, if we have two of them, we could say diene or triene, that type of thing, okay? So looking at some examples, again, these come out of your big booklet. So here we have a line diagram, right? I showed that to you in the very first lesson, and then we haven't seen too much of it since then. Okay, we're going to start to slowly incorporate some line diagrams into some of the stuff that we do. So we talked about when we looked at them how there's a carbon at the start and end of every line, right? So there's some carbons here. There's also a carbon where there's a bend. Okay, generally you're going to find that there's also bends here and here, but because this is a triple bond, the particular program that we use draws it actually in that three-dimensional shape, and whether you do that or not is not a big deal. But what you're going to find is there is technically a carbon here as well as here, right? And when we first talked about line diagrams, I said where it starts and ends and everywhere that there's a bend. Okay, triple bonds are the only exception where you're also going to find that there are some carbons right here, okay? Kind of the way you know that they're there is this triple bond doesn't extend all the way to here, and it doesn't extend all the way to here. So we have 1, 2, 3, 4, 5 carbons in that main chain, okay? So based on the fact that we have 5 carbons in the main chain, we know the root is going to be pent, okay? Our suffix, because we have a triple bond, is going to be that -ine, Y-N-E. We need to include a number with it. So same as before, we check both sides for numbering. So if we start on the left side, 1, 2. I start on the right side, 1, 2, 3. Because 2 is less, we're going to choose to number from that direction. So this is going to be a pent dash 2 dash I. I don't need a prefix. And the reason I don't need a prefix, I don't have anything going off of this, right? It's all part of that longest chain. The other thing I know some of you guys like to do when you get these line diagrams, especially when they're new to you, sometimes you guys just like to look at them and draw your own kind of condensed structural from it, right? And be like, okay, well, here's that first C from that. Then I know I have a single bond to my next C, which is this one. Then I know that I've got a triple because I can see that in my picture. Then I've got this carbon here, right? Then we've got a single bond to another carbon, and then that last single bond to a carbon, right? And obviously I have all my H's in there that I haven't put in, but sometimes this can help you to make it a little more obvious, like, oh yeah, now I see why there's no side chains, why it all goes in a straight line. So if ever you're struggling with the line diagram, definitely nothing stopping you from drawing kind of off in the margin what that diagram would look like as a structural or condensed structural, okay? All right, next example is this one. This is number 2 in your booklet, okay? So this one is kind of a hybrid. I don't want to say you don't see these that often, but you don't tend to get them too often. So there is technically a carbon here and a carbon here, okay? And the way I know that is I have H's attached to them. Oh yeah, and right here and here, okay? So I gotta start by finding my longest chain because that's what I always do. So let's check straight across. 1, 2, 3, 4, 5, 6. If I did something different, 1, 2, 3, 4, that's not more. 1, 2, 3, 4, 5, also not more. So that means my longest chain is going to be that, okay? So numbering wise, if I make this carbon 1, I have a double bond right after 1. If I start over here, this is 1, there's nothing special at 1, this is 2, I have something happening here, but because a 1 is smaller than a 2, we're going to choose to number from this side. Sometimes guys get confused with this one. You're like, but that's a triple bond, Miss Chip. You should have started numbering on that side. The problem, though, is that triple bond isn't until carbon number 2, which means there is no tie, so it's not about order of priority. It's about the lowest possible numbers where this double bond here is right after carbon 1. Okay, so again, when we're coming up with a name, we have 6 carbons, so we know that our root is going to be hex. Okay, we only have one side chain, right? We have this side chain right here. It only has 1 carbon in it. That means it's a methyl. Okay, because it is attached to carbon number 3, that means our prefix is going to be 3-methyl. So we have 3-methyl hex, right? 3-methyl for this, hex for this. Now we need to get to our suffix. So we have 2 double bonds and a triple bond. They all need to go into that ending. So alphabetically, these are enes, and this is an ine. So we're going to put the enes first. We have 2 of them. So because we have 2 of them, it's going to be a diene. Okay, it's between carbon 1 and 2, so we're going to say it's a 1. And then the next one is between 2 and 3, so we're going to give it a 2. So we're going to have dash 1, comma 2, dash diene. Okay, and the 1, comma 2, because one's at 1, one's at 2. And diene, because there's 2 enes, comma, because we separate numbers from numbers using commas. And a dash, because we separate numbers from letters using that. Okay, then last thing we need to do, obviously, is put in that triple bond. It's between carbon 4 and 5. So we're going to say dash 4, dash ine, because we're always using that smallest number possible. Okay. All right, again, one going the other way. So this is number 1 off the list that you have. So it's a hex. Okay, we're going to change things up a little bit here. We're going to do a line diagram to show you what it looks like to do this as a line diagram. Okay, so because hex means 6, we're going to start. There's 1, right? Carbon 1 is here, carbon 2 is here. Now we have 3, now we have 4, now we have 5, now we have 6. Okay, we generally tend to do that main chain kind of as like that mountain range, right? So carbon 1, carbon 2, carbon 3, carbon 4, carbon 5, carbon 6. Okay, then we look at this. It was a 1-ine, so that's telling me that after carbon number 1, I need a triple bond. So this is carbon number 1 here. So I'm going to throw this in as a triple bond. Okay, then we have a 3,4 dimethyl. So that means at carbon 3, we have a methyl. So 1, 2, 3. Here's carbon 3. So to indicate a methyl, which is just one carbon, just one thing sticking off, okay? Because this is still that carbon that's part of the main chain. Here's my 1 carbon. And then 4 also needs a methyl, so we're going to do the same thing, okay? I could have technically squeezed those side chains into this area, but it's sometimes easier just to put them where you have those big open gaps, right? So looking at this, 1, 2, 3, 4, 5, 6, there's my hex, 1-ine, 3 methyl, and 4 methyl. Okay, it takes a little bit of practice drawing these, but they're definitely much faster. And so they do tend to get used pretty often just because they are faster to draw. You don't have to worry about your H's because they are implied to be there, okay? All right, last thing is properties of alkynes. So just like alkanes and alkenes, these are nonpolar. That means they don't dissolve in water. So what we find they do dissolve in is hexane, okay? So very similar to those other ones that we were dealing with. They are soluble in hexane. So when we think about intermolecular forces, these guys, just like alkanes and alkenes, have only London dispersion forces. So London dispersion forces, if you remember back to last year, how strong they are dependent on 2 things. The first thing is the number of electrons, right? The more electrons I have, the stronger they're going to be. The second thing is the shape. And what we find is the more linear the shape is, the more contact area there is between them. So the stronger that attraction is going to be. So when we started looking at our melting points and boiling points, we started with alkenes and we popped them like this. And we said, as we increase the number of carbons, the melting point and boiling point is going to increase because we have more electrons. Then we took alkenes and we put them down here. And we said that alkenes were below alkenes. And the reason that they are below alkenes, I kind of got cut off, I ran out of time on that one, is because they have fewer electrons. Okay, and the fact that they have fewer electrons means that they have a weaker London dispersion force. So based off of that trend, you would expect that, sorry, I'm trying to find a different color here, the alkynes would fit in down here, right? You'd be like, well, that makes sense. They have less electrons, so they're going to have a weaker LDF. But what you actually find is that alkynes fit in up here, okay? And the reason that our alkynes are going to fit in up here is because it's not just about how many electrons you have. It's also about your shape. Okay, so although they have fewer electrons, they have a more linear shape. That actually means that they have stronger LDFs than those other ones do. Okay, so when you're ranking things, which we definitely do, alkynes are above alkanes, which are above alkenes, okay? Started with alkane. Alkene was less because it has less electrons, so weaker LDF. Alkyne, because of that shape, even though it has less electrons, the shape gives it a stronger London dispersion force. So if you were asked to compare, let's say, ethane to ethene to ethyne, you would want to know that that ethyne would be the highest, then it would be ethane, then it would be ethene, okay?